Hello friends, this is Yogesh Popat and today again we are here with a very important topic from the portion gravitation. So today we are going to discuss about Kepler's law, which is applicable for planetary motion when the planets revolves around the sun. So we are going to see the different parameters of the revolution of planet around sun. So there are three laws of Kepler's for planetary motion. The first is law of orbit, second is law of area, and third is law of time period. If we discuss the first case about law of orbit, I have uploaded one more video on this gravitation part, that is with the simulation. So there also I have explained this part. So if we see the first topic, that is law of orbit. So the Kepler's first law, that is law of orbit, says that the planet, which is indicated by P here, revolves around the sun in an elliptical orbit, not in circular orbit. Generally, when we derive the different equation for gravitation, if we talk about the gravitational potential energy, if we talk about the acceleration due to gravity, we generally take the circular revolution, exactly circular revolution of the planet around the sun. But that is not the case. We take it just for the simplicity, for the easiness of the derivation. But the actual structure of the trajectory or the path of the planet around the sun is elliptical. So the first law of orbit states that the planet revolves around the sun in an elliptical orbit with sun at one of its focus. There are two focuses are possible in the ellipse. So here I have considered sun to be at one of the focus. You can consider it here also if you want. Okay, so the law of orbit states that the planets revolve around the sun in an elliptical orbit with sun at one of its focus. If you see here, this distance is the closest distance from the sun. The distance is not even. Sun is near to this point and farther from this point. So the nearest point with respect to the sun is called perigee, which is also termed as perihelion, whereas the farthest point from the sun in this elliptical orbit is called apogee, which is also referred as ephelion. The two important parameters are there, the two important terminologies are there. If I join these farthest points, the straight points, the longest distance of the orbit, this is called major axis. Let me label it as AB. This AB is called major axis. And if I join the closest points, that is the shortest distance between the two oppositely paired points, let me label it as CD, and this CD will be termed as minor axis. So this AB is the major axis and the CD is the minor axis. If I plot this point O, and if we take this distances from the center, so this will be semi-major axis and this OC will be semi-minor axis. So these are the different terminologies which we generally use in the Kepler's law of orbit. Again I am stating it, law of orbit states that the planets revolve the sun around the sun in an elliptical orbit with sun at one of its focus. Perigee is the closest point of the orbit with respect to sun. Apogee is the farthest point on the orbit from the sun. Major axis is the largest distance that can be plotted between the oppositely plotted pairs of points, and CD is the minor axis, which is the shortest distance in this orbit. So this is what we call law of orbit. Coming to the next part, that is law of area. Suppose again this is the elliptical orbit and this S indicates the location of sun. If the planet at certain instant at point A, and if it takes time t1 to reach to point B. So if I join these 2 points from the sun, this is the area that we are getting. Let me shade this area and let me label it as A1. This triangle, you may say this is not a perfect triangle because this is the arc, but let me say it as a triangle. ASB forms the area A1. at certain instant this planet has reached to point C, and from point C to point D it is taking time t2. So if I join again this point C and point D, this is again a region is formed, and let me consider this region with area A2. If the time taken to move on the orbit from point A to point B is same as the time taken by the orbit to move from point C to D, that means if I say if T1 is equals to T2, then A1 should also be equals to A2. That means the line joining the sun and planet sweeps out or covers equal area in equal interval of time. Now what is the reason? Because see, from here if you see the distance is more, from here if you see the distance is less, this arc is less as compared to this arc. So how these areas are becoming same? This is one question that should strike your mind. So the answer is, at this point the speed of the revolution of the planet will be less. That's why it is covering a lesser arc, but the distance is more. Why? Because Newton's law of gravitation says that F is equals to G m1 m2 upon r square. m1 you can consider the mass of the sun. This is one body. The second body is the planet, that is m2. So you can see here F is inversely proportional to r square. That means with the distance the force of gravitation decreases. So more will be the distance, less will be the force of gravitation between the sun and the planet, and due to lesser force acting on the planet or lesser force of the gravitational force between the sun and the planet, the speed of revolution of the planet will be less. But if you take this part, here the distance is less, due to which the force of gravitation will be more, and when the force of gravitation will be more, the speed of revolution will be more. So here it is covering a greater arc as compared to this arc, and that is why due to change in the distance, if this time period, that is t1 and t2, the time duration, not time period, the time duration will be same, reaching the point from point A to point B or from point C to D. If this duration is same, so the sweeping area, the area swept by the line joining the sun and planet will also be same, that is A1 is equals to A2, provided T1 must be equals to T2. And the reason I have indicated you here, more will be the distance, lesser will be the force of gravitation, and lesser will be the speed. Coming to the third point, that is law of time period. Time period simply means the revolution of the planet takes a certain duration to complete one revolution. So time taken by the planet to complete one revolution around the sun is called time period. So this law states that the time period, the square of the time period, that is t, again this is the elliptical orbit. So the square of the time period will be directly proportional to the average distance between the sun and planet. Why we are saying average distance? Because the distance is variable at every point. The distance will be different for the planet. This is not a uniform circle. This is an ellipse. So the average distance we are taking because the distance is variable with respect to sun and the planet. So the square of the time period will be directly proportional to the cube of the average distance between the sun and the planet. So these are the three important laws. In class 11, the derivational part is also there for law of area and law of time period. Maybe in the next class we will prove that also. So just recall it once again. Three laws are there: law of orbit, law of area, law of time period. Law of orbit says that the planet revolves around the sun in an elliptical orbit with sun at one of its focus. The second law of area says that the line joining the sun and the planet sweeps out equal area in equal interval of time. The third law, that is law of time period, says that the square of the time period is directly proportional to the average distance, that is r here, cube of the average distance between the sun and the planet. So this is all about the basics of laws of Kepler for a planetary motion. In the next class we'll have the derivational part also. Thank you so much. Thank you.